Okay, so thanks everyone for coming. So I guess maybe this will be the last virtual perspectives. So the idea today was that we were gonna go over the fall course offerings in the math department and kind of talk about pass through the major and the proof-based class offerings and kind of how to build a major since Rice offers maximal flexibility. So I'm Professor Joe Nelson. I'm not teaching in the fall, but I'll be teaching in the spring, and I'll say a little bit about that class at the very end. So I first wanted to introduce Professor Orkan, and she's going to be explaining the introduction to proof-based classes and how that kind of works at Rice in terms of the course offerings. And let me put the course offerings in the chat in case it's helpful for people to follow along. Okay, I can't put it in the chat, so never mind. You can just go ahead, Professor Orkan.
Thank you so much and welcome everybody. I hope that you are enjoying your Monday right now. As the math department, we are offering some introduction to the proof-based classes. Whenever you see an honor code in front of, for instance, the class, it means that you are actually, you will be exposed to the proof-based theorems or proof-based class through the semester. So honors linear algebra, where Professor Wolf will be talking about, or honors differential equations, honors calculus sequence are the parts that you can really introduce. I mean, you can learn about the proofs or how the analytical thinking is embedded on the theorems and the proofs of it. You will be just experiencing those in these classes. And when I talk about, I mean, or when you see that honors courses, it might be a little bit scary at the beginning, but please give it a chance to these classes. One thing that we can also guarantee you is that hopefully, I mean, everything will work fine. But if you feel like you are, you didn't like the format of the class or the flavor of the contents, you can always drop down to the regular based version of that class. So honors differential equations versus just ordinary differential equation classes. And up to those years, it was the first 6 weeks of the semester, you can just drop down to the other class. But with the COVID, I think there was some extensions on that. I don't know what will be happening with the coming fall semester, but I can assure you that, I mean, you will be having time to drop down from one class to another. This is also true for the calculus classes in general. And you will be also getting more information about these other classes through the talks also. Thank you.
Thanks, Professor Orkan. So next, I was gonna have Professor Wolf talk about honors linear algebra, because I think that's the main proof-based class that's being offered in fall 2021.
Yep, I think also probably Math 221 is also offered, but which is the honors vector calculus class. But so I'll be teaching, I'm really looking forward to this, honors linear algebra, Math 354. So I'll make 2 comments about this. This is linear algebra. This is like one of the, I'll say something out loud and see how many of my colleagues grimace. This is one of the, in some sense, 2 pillars of mathematics, linear algebra and calculus. Tremendously important, tremendously useful. It's always hard to describe what's the content of a math class, because if you know what I'm talking about, you don't need the class. But in some sense, you start with simultaneous, we were used to solving simultaneous linear equations. And so why does all that work and how should we imagine it? What the course does is it builds up from the very foundations, both Math 354 and Math 355, build up from the foundations of the subject, studying things called vector spaces and all of the structures that are involved with those. There's a beautiful theory that is somewhat geometric, somewhat algebraic, and tremendous applications, matrix manipulation that find expression across the intellectual landscape. So, so just a great subject. The difference between Math 354 and Math 355 is that 354 will be theoretical. So we will explain why everything is true, and we will explain it through proofs, and you will understand it through proofs. At the same time, there'll be some computational problems. You have to know how to actually work with these things later, but everything will be proof-based. It is a first proofs course. So I want to like stare everyone in the face and make sure this is clear. It is a first proofs course. I will not assume anyone in the class has ever written a proof, knows how to spell the word proof, anything. So we start at the foundations, and and it could be that 95% of the class is well experienced in proofs. I don't care. We're going to presume that people have never written a proof before and build up from there. So, and this is a great facility to learn. It changes how you think about the world. It changes how you hear conversations. It changes how you write. And it is what mathematics is how we understand mathematics, is how we investigate. So, so it is a course to introduce you to proofs and to use them in the development of this beautiful theory.
And okay, great. And I guess one thing I wanted to point out about honors linear algebra as a proof-based class is that it will get you into other classes a little bit faster than going through honors calculus will, because the algebra sequence requires algebra or linear algebra as a prerequisite, and it also typically requires that you've seen a little bit of proof writing before. And so I wanted to kind of advertise honors linear algebra as getting that extra experience, and then also the nature of the proofs is a little bit different than the nature of the proofs in the honors calculus series. So
yeah.
Okay.
One thing that might be pointed out is there is also a dropback provision from 354 to 355.
Right.
And then, the next person is Professor Wong, and he's going to talk about pass through the major and the undergraduate teaching practicum offering.
All right. Yeah. Thanks, Joe. Yeah. So as what has been mentioned, you really, in order to start through the major, you really do want to get a first proofs course in as quickly as possible, because that opens up pretty much everything else. And once you have a first proofs course, and then I would say along with Mike, that linear algebra is really one of the biggest keys. So you have a first proofs course and you have linear algebra, then I would say that the two biggest priorities are real analysis, which is Math 321 or Math 331, which will be talked about in more depth in a little bit later, and then abstract algebra also. But those are the two biggest core courses that I personally encourage every math major to aim for as courses beyond linear algebra. But they do require you to have some proof background, and for abstract algebra, you definitely need to have some linear algebra in your back pocket. And then once you're beyond that, then the world is your oyster, so to speak. There are a fair number of courses beyond Real Analysis 1 and Abstract Algebra 1 that have one of those two as a prerequisite. And so, if you're able to get those under your belt by, say, fall of junior year, you have a lot of opportunity to take interesting higher level electives. But if not, that's fine too. There are also plenty of electives that don't require either one of those. But I would say it's about 50-50 in terms of whether an elective might require an analysis or algebra prerequisite. So like I said, people will talk more about those courses a little bit later. There's also Math 280. This is particularly of interest to anybody who might be thinking of going into teaching. So many of you who have gone through some of the calculus courses, especially a lot this past year, may have done some in-class activities with TAs. And some of the TAs have been graduate students, but some of the TAs have also been undergraduates. And this is a program that we've started this past year. It actually was planned before we knew that COVID was a thing, but this is just an opportunity for undergraduates who are interested in learning more about a particular subject by teaching it, to get some hands-on experience in working with students in class. And so I don't know exactly which courses next year will be in need of undergraduate TAs, but there will definitely be a few. And so if you're interested in that, I would shoot me an email, and I'd love to talk to you more.
Thanks so much, Professor Wong. And then the next person is going to be Professor Lukic, and he's going to be talking about both the undergraduate and then the cross-listed graduate analysis offerings that he's teaching this fall.
Thank you. Yeah. Hi, everyone. So yeah, so I'll be teaching Math 321, which is the analysis one, which in one sense, this is a kind of rigorous look at the mathematics behind calculus. And the course starts with things like, well, it starts with the axioms for real numbers. What do we think analysis, what are real numbers? So we start with the axioms and we build from there. And so part of the course is revisiting some notions that you already seen from calculus, some limits and derivatives and things like that. But the course also does a lot more. So, so one thing is that because it's a rigorous look at it, there's some things that in calculus can be a little bit of a mystery. And this appears when you, for example, when you get to Taylor series, you expand something as you get Taylor polynomial of a function, and then you want to know when can you turn this into a Taylor series, and when does that Taylor series actually give you the function back? And in calculus, you typically see just these isolated results that, well, for this function, it works out, or for that function, it works out. But if you want to have a more robust understanding of that, you really need a rigorous look at it, kind of from the ground up. So one aspect of the course is that. The course also takes a look at a slightly more, kind of a slightly more abstract look at something called metric spaces. And so these metric spaces are really an underpinning, one of the pillars of math, right? Maybe not quite like linear algebra, but also, so metric spaces are just a general way of saying, I have some set together with some function that tells me the distances between the points in the set. And so you're used to measuring distances in a Euclidean space. But once you have an abstract look at what is a metric space, then you realize you can apply that to other situations. So for example, you can apply that to say, I want to measure the distance between two functions. And so that leads you to these notions like uniform convergence, for example, uniform convergence of functions, which again is important. And so, and through that, once you study metric spaces, in that there's some amount of new terminology in ideas like when some set is connected or compact or something like this, which is just terminology that you need for anything you want to do, anything else you want to do in analysis. But also if you want to do something like geometry, it's hard to do geometry if you don't know what a compact set is. So yeah, it's kind of, I think, one of these things we would consider foundational courses. So yeah, so that's Math 321, Analysis 1. And then I'm also teaching Math 425, which is integration theory, which is really, it's an introduction to measure theory and integration theory. And it's more precisely, it's really this theory of Lebesgue integration. So the object that you learn in calculus is the Riemann integral. And it's the Riemann integral because you take your piece of the real line, you divide it into some pieces this way, and you kind of compute the area under some function. And that has nice properties. You know, a sum of integrals of two functions is the integral of the sum and things like that. But Riemann integration really has shortcomings when you try to take limits. And beyond a certain point, you really kind of have trouble if you want to take limits and integrals in the same sentence. So this is one thing where Lebesgue integration really shines. So that becomes, so there's the central notion is that of assigning measure to sets, which again can be done very concretely. You can be on the line and you can start from this idea that a measure of an interval is the length of that interval, and you can build that up to a very robust notion of measure on the real line. You can also do it more abstractly, and we do a combination of the two. One other way to motivate this is that this also gives you, so because this Lebesgue integral has a much better properties under convergence, it's so now for those of you who have already taken some analysis, if you have continuous functions on an interval, and if you take the distance between f and g to be the maximum of f minus g, you may have learned that that's a complete metric space. But if you have two continuous functions f and g on an interval, and you'd say, I want the distance between f and g to be the integral of absolute f minus g, you get another metric. So you get another metric space with continuous functions, but that metric space is not complete. So Lebesgue integration turns out to be perfectly placed to answer this question of what's the completion of this, right? So, okay, through that, Lebesgue integration also is indispensable for studying things where you want to study convergence, but you don't have typically uniform convergence. So just as in analysis one, one of the centerpieces of that is Taylor series in some sense. And Taylor series, typically some of you have taken it, will at least know that Taylor series, often when you're inside your radius, Taylor series tend to converge uniformly there, right? So that's perfect because you can study that in analysis one. But if you want to study something like Fourier series, well, Fourier series typically don't converge uniformly, or rather that's not the most natural setting for studying Fourier series. So again, so maybe I'm using jargon that you don't know, but so Fourier series are if you have a function on an interval and you want to decompose it, not in terms of polynomials, but you want to decompose it in terms of sines and cosines, basically. So Fourier series, many of you first see them in a physics class or even somewhere else, right? I mean, they're ubiquitous. Fourier series, Fourier transforms, they're ubiquitous in applications in physics and engineering and everywhere. But if you want to study them mathematically and if you want to have nice, robust results, you really want something more robust than uniform convergence. And that's exactly the kind of thing we do in Math 425. So yeah, that's about it for me. I like teaching both courses. I hope that you'll enjoy taking them if that's your preference. So.
And then Professor Lukic, could you say something about the difference between 331, which is honors analysis one, and Math 321, which is real analysis one?
I'm gonna punt that question to Dr. Sams.
I guess you've only taught 321 before, so.
Yes, exactly. So I haven't taught 331, and so he will be able to make a better contrast.
Okay, cool.
Thanks.
Thank
you.
Then, the next in analysis offerings while we wait for Professor Sams to come is Dr. Nikome, and she's going to be talking about her Intro to PDE class, which she'll be teaching in the fall.
Great, thank you. So hello, everybody. So actually there is an easy way to also connect it to what was being discussed earlier. So this class is going to be Introduction to PDEs. I think the only recommended prerequisite for this class is 211, an OD class, but some knowledge of multivariable calculus would also be nice, but not absolutely necessary. I think it will be accessible. Well, it will be accessible to both people that have some experience with proof writing and also to people that don't. There will be some very easy proofs, so it will sort of warm you up maybe for your next proof-based class. Now the content is will be a little bit different than what you are probably seeing online. So what we're going to do is focus on the three classical PDEs, three classical examples of PDEs, the wave equation, the heat equation, and the Laplace equation, and study them in a variety of settings, motivate why they're interesting and where they appear in nature. You might have seen them in a physics class before, so now we will actually do math with them. And we will both actually learn how to solve them in different geometries, study some of them, of their qualitative properties, and also develop a lot of techniques that are very useful both for these particular examples of PDEs, but also in general for PDEs, like Fourier series. Yeah, so it's a very interesting class, I think, and I think it will be very interesting and useful both for people that are interested in exactly in math, but also for people that are interested in physics or engineering. Yeah, I was teaching it last year and I really enjoyed it, and I hope you will enjoy it too.
Okay. Oh, and then Professor Lukic has to go. So if anyone has questions for Professor Lukic, now is a great time to ask. But no one ever wants to ask questions in the middle of a Zoom meeting. Okay, so we'll change gears a little bit, and Professor Orkan is going to discuss the directed reading program, which I think is math.
So let me post the link for the web page. It's over here, directed reading program. It's under the Math CDU. It's a little bit tricky to find it, but I will be making sure that it's going to be, popping up easier in, coming weeks. So in the directed reading program, we are trying to offer, as the math department, you the experience of doing reading / the research in math. Starting to the research in math is a little bit challenging because we need to make sure that your background will be enough to do some, research in math. But these directed reading programs are very good tools, or they are going to be opening the doors for you to experience math and reading some literature in math with your mentor. So this program will be pairing you with either a graduate student or a postdoc from the math department, and then you will be, through the semester, you will be reading together on some specific topics of your choice. So this semester I was hoping to start this program, but I couldn't make it happen. I'm hoping that starting with the summer term, we will be able to offer you this program. Yeah, so directed reading program, exactly here. So when you look at the Math 490, you can also think of it as a credit-based course. So you have two options here. Either you can take these classes as a credit course through the summer, during the summer, or during the regular terms. Or in the directed reading program, it's not going to be counted as your credit. So it's going to be a non-credit course. I don't want to say also a course, because you might be thinking that it's by the credit, but it's a program that you will be really reading some math topics. So when you go to this directed reading program web page, you are going to be seeing in a couple of weeks a link that's also showing you the sign-up sheet. So if you are interested about this reading program, please sign that up. I couldn't really respond to that this semester, and I'm very sorry about this. But starting with the summer term, we are going to start this wheel. With the fall, I'm hoping that actually it's going to be, more structured. And I'm hoping that you will be all experiencing this. The requirements are, depending on the topics, and with your mentor you are going to decide the subjects. We are expecting you to Thank you so much, Dr. Nelson. So we are expecting you to meet with your mentor at least 1 hour, maybe 2 hours in a week. And then you will be also additionally reading 2 to 3 hours a week about the given topics. And then this will be really ranging or taking your time up to 4 hours every week. I'm hoping that it's not going to be too much, but I'm also hoping that it's going to help you a lot with the, exposing to the research cores of math. Okay, so if you have any questions, again, you can reach to me anytime that you would like. I will be here. Okay, thank you.
And then we'll move on to the algebraist. So Professor Walton will start by talking a little bit about the algebra sequence, which just got redesigned this past year. Oh, you have to oh, sorry, yes.
All right. That's usually what I do. I talk on mute until somebody tells me not to. All right, so I'm Chelsea Walton. I'm new to the university, and I was tasked with compiling the algebra sequence. Now we have a full year of undergraduate algebra and a full year of grad algebra. Now, undergrad algebra is 356, 357. I'm currently teaching 357 this semester. And grad algebra, which you can take as an undergrad, is 463, 464. But you need undergrad algebra in order to get into the grad sequence. So what's the difference between the two courses? I'll just discuss what's going to happen in the fall briefly. I'll let Dr. Frey talk about this in detail. But essentially, what is algebra about? It's about structure. It's about structure. And for a given structure, you might want nice operations on a collection, let's say a collection of objects. So for instance, you might be interested in a structure that has an addition, one that has a subtraction, a multiplication, and a division. And whenever you have a combination of certain operations, it gives you a different structure. So the first structure that you're going to encounter in both of these courses is a group. But in 356, you're going to spend about 2/3 of your time on groups, really building up that foundation of group theory. Okay. And then after that, you'll spend the remainder of the course talking about rings, which is basically a special type of group that has an additional operation. Now, in the graduate level, not only are you going to cover groups for only half the time, 1/3 of the class, you're going to cover rings and also modules and vector spaces. Okay. And then on top of that, usually what I'll do, if I'm teaching the course, I'm going to stick in about a week's worth of category theory, because this is something at the graduate level you should learn in some course, and usually it's taught in an ad hoc way. So I'm going to try to make it a part of this course just for 1 week at the end, probably extra credit homework or something like this. But I think this is a material that no matter what field you end up in, you're going to run into this stuff. So that's the difference between the two classes. Undergrad algebra, you're going to cover groups and rings. Grad algebra, you're going to cover all this stuff in green. Now you might be wondering, okay, well, what about these other two structures? Well, these are covered in the spring courses. All right, any questions on this? Try not to go into detail about what these structures are because that's the course, but you can get a sense of it from this cartoon. Okay.
Thanks, Professor Walton. Okay, so we'll switch to Dr. Fry, who's going to tell us about the first semester, which is Math 356.
Yeah, great. Okay, hey everyone. So I'll be teaching Math 356. This is Abstract Algebra 1, which was the first class that Dr. Walton was just talking about. The prereqs for this class are linear algebra, and then one of the courses that was talked about at the beginning, that's one of the sort of introduction to proof classes. So, so the class will be very proof-based. Homework will sort of expect you to write a lot of proofs and develop that sort of proof intuition through algebra. In terms of the content of the course, like Dr. Walton said, this is about looking at structures. And so the sort of two structures we look at are groups and rings, which is sort of in terms of that flow chart, we're sort of starting at some of the least amount of structure that you might be interested in. And so in groups, what you have is some sort of addition law where there's also a subtraction, so things have inverses, and there's an identity element. And then you can ask sort of, can this group have more structure? Like, is the addition commutative? And that was abelian groups was sort of the next thing on that flow chart. And so, as she said, we'll spend a lot of the course talking about groups, maybe thinking about sort of what other properties do you get from just this simple structure? How do these groups arise? So looking at subgroups, looking at quotient groups, products of groups, symmetry groups, and then group actions, which is where if you take a set, then there's sort of a way to define an operation between the group and the set that produces another element in the set. And then the last third will be looking at rings, which is taking, say, a commutative group and adding a multiplication to it. So sort of adding one more level of structure. And we'll sort of, again, go through some of these things, like how do these arise, looking at ideals and then quotients, and then looking at rings, which have, again, a little bit more structure, not necessarily in terms of sort of moving to a different place on that flow chart, but in terms of maybe they have unique factorization, or maybe all of their ideals are principal or things like that. So they can have some extra structures in that way. Yeah, so I think that's sort of the content. I think it's a really fun class. It's a good introduction to algebra, and yeah, maybe I think it's sort of a common prereq for other classes, but also algebra just sort of shows up all over the place in lots of areas of math. So it's a very useful tool to see. Yeah, okay, I think that's all.
Cool. So now is the fun part where we have two faculty who are still in meetings and haven't joined the meeting, and they're the last two to talk about classes. So I guess I'll say that I'm teaching Math 401 next spring, which is curves and surfaces. It's a really fun class because we get to actually prove some theorems about the classification of surfaces. And a lot of times when you see a differential geometry class, it's an entire semester of definitions, and it's extremely dry and kind of hard to get a sense of what you're doing. But in this curves and surfaces class, you can use kind of the power of multivariable calculus to attack problems that have really deep generalizations. So it's I really enjoyed teaching it a lot, and it satisfies one of the BS requirements for geometry. And it has the only prerequisite for it is Math 321 or 331, which is the real analysis class. So I just wanted to recommend, if you're not like super gung-ho about taking analysis in the fall, but you really like geometry and topology, and you want to get to kind of some more interesting geometric topics, to take Math 321 with Professor Lukic in the fall. And it's always a great idea to get linear algebra done so you can start doing the algebra sequence, because it's really exciting. So that's kind of why everyone's always saying take Math 321, take Math 354. And that's because it just basically opens the doors to all the later classes, and you get to start to see some really kind of cool and exciting and more creative mathematics than just okay, let's like grind through these problems and like do these computations. And I'm not sure exactly what to do. So what I'm going to do is I'm going to pause the record. What?
Am I supposed to go again for grad
algebra?
algebra?
Oh, sorry. Yes, you are supposed to go again for graduate algebra.
I'm just trying to eat up time for you.
Yeah, so you can go again and explain graduate algebra.
Wasting time. Okay, let me know how slowly you want me to talk, because I could drone on. Okay, I'll go again. Grad algebra. I taught this last fall, and I think the course is going to go pretty similar to the way it ran this fall as it ran last fall. Last fall, I did a flipped classroom. I recorded all the lectures, and we had discussions in class. I have to think about whether I want to keep that format or not in person. I don't know. But the content of the course will be pretty much the same. Again, it's going to be 1/3 groups. So it's about double pace at what Dr. Fry is going to teach, but again, it's a graduate level course and you need undergrad algebra to get into it. And we're also going to cover some topics that aren't traditionally covered in undergraduate algebra, like semi-direct products, P groups, nilpotent groups, presentations of groups. I mean, that can be new. But and then also there are some topics that are covered in undergrad algebra, but they come pretty early in the course. So like I said, I highly recommend this course. I think it's fun but only if you have the preparation. Only if you have the preparation. If you don't, take 356, because 356 is going to be an awesome course. Now, after that, we'll spend about 2/3 of the course on rings. Again, there are some topics that aren't covered in undergraduate algebra, like Grosvenor bases, maybe a bit more detail of quotient rings. That's my dog snoring, sorry. And then we're going to cover module theory. Now, module theory is covered in 357, but what's new in this course is we'll cover tensor products and modules over PIDs. That's stuff that you won't see in undergrad algebra. And then lastly, the last week on category theory. What is a category? A category is just a collection of objects and maps between them. That's it. That's, you can take all your structures and all the structure preserving maps, and you could talk about categories of any mathematical objects you like. And it gives you a way of transporting one framework, say like analytic framework, to an algebraic framework, to a topological framework, to a geometric framework. It is really beautiful stuff. So that's why I will introduce this material here. Okay, did I waste enough time?
No, neither of them have joined yet. So maybe what I can do is I'll pause the recording and then people can ask questions. And then I think Professor Leininger should be here in about 5 minutes, and hopefully Professor Sems will come, because I too wanted to know what the difference between Math 321 and 331 was. So here, I'll.
Oh, and Leininger is here.
Yes.
There we go.
You have to unmute yourself, Chris.
Hi.
Oh, you're still. Oh, never mind. Okay.
Was I supposed to say more?
Oh, can you say a few words about what's in geometric topology?
Oh, sure. When I got on, Chelsea was talking. I thought maybe she was still.
Oh, sorry. We were killing the time. We.
I see. Okay. Very good. Yeah. So I'm teaching this geometric topology course in the fall, and kind of just experimenting a little bit last semester. And I think what it'll be next semester, though, is kind of a good place to connect group theory with ideas in geometry and topology. So mostly because that's kind of how I like to think about things in geometric topology. And so it'll be a good lead in to the algebraic topology course in the spring, which is more of the sort of classical algebraic topology, homology and cohomology theory. So I will talk about covering spaces and fundamental groups, which involves things like nice spaces and nice actions of groups on those spaces. And it's kind of the first stepping stone into algebraic topology. So that'll be sort of part of the class, and then the rest of the class will be talking about some interesting spaces from geometric topology. So for example, surfaces, we'll talk about the classification of surfaces, which many of you may have seen. We'll see why that's true. And then we'll also talk about some other things in geometric topology that are more closely tied to group theory. Specifically, I want to talk some about geometric group theory. So covering spaces and fundamental groups, they go hand in hand, and it's kind of one of the things that really informs geometric group theory. So geometric group theory is about groups acting on spaces and trying to understand the groups from their actions on spaces. And so the fundamental group acting on a covering space turns out to be a good model for a lot of the things that happen in geometric group theory. So so we'll talk about some ideas in geometric group theory, and then one other topic in sort of geometry and topology, which is various kinds of geometric spaces. So we'll talk about hyperbolic space and Euclidean space and spherical space, and then we'll sort of connect that to things like geometric group theory and to covering spaces and fundamental groups. So I'm not sure what, since I didn't hear what everybody else said about their courses, I don't know what kinds of things you were talking about. So maybe if you guys have any questions about the specifics about what's in there, or what you should know before you go in, feel free to ask.
Well, I know of some students who are curious about what the prereqs are. Like for instance, like new grad students who are going to take your course, their preparation is going to be all over the place, I imagine. So what do you expect students to know beforehand?
Yeah. So I would expect students to know a little point set topology. So you can get by in geometric topology without knowing too much point set topology, but knowing what a topology is, knowing what continuous functions are on topological spaces, properties of topological spaces, compactness, connectedness, and that's pretty much it. So something like, I forget which chapter, but
Moncrief, like chapter
yeah,
2 Moncrief?
yeah, like chapter 2 of Moncrief, exactly. Yeah, that's plenty for what we'll do. But it is important to have seen those concepts before you come in, because it's not that much material, but it's too much to try to cover in the beginning of the class.
And then I think the other prereq for Math 444 is abstract algebra 1, because you have to
Oh.
talk about groups and group actions and normal subgroups. And
Absolutely. Yep, for sure. Yep. And those two things.
okay. And then we'll round out the meeting with Professor Sems, who will tell us a bit about honors analysis 1, which is Math 331, and kind of what the difference between that and Math 321 is.
Yeah, so maybe I should start with the second, since that's always comes up. And just as a technical point, of course, which is in some ways sort of like the technical points one might discuss in class. Of course, I can't say exactly what the difference is because I don't know exactly what Lukács is going to be doing, and that can vary a bit. But in practice, I would say one of the differences, so in Math 321, at some level, we sort of start over in a way that, although part of the motivation is something like the theory behind calculus, at some level, we start over with very fundamental things like the definition of a metric space. So you don't have to know the definition of metric space. That'll be something I would discuss on the first day. There are also some basic properties of the real numbers that I would usually go over that are discussed in chapter 1 of Rudin's Principles of Mathematical Analysis at length. Some students taking 321 or 331 may have taken Math 302 here, in which case they probably have heard a lot of that kind of thing. But some students might have taken other classes like Math 221 or the Honors Vector Calculus class, or Honors Linear Algebra, Math 354. So they would have had some exposure to proofs and maybe some degree of abstraction. All of these things are sort of relevant for the classes. But one thing that can be a little bit tricky is that different students may have slightly different backgrounds in terms of exposure to abstract mathematics, but not so much of nitty-gritty with epsilons and deltas, or exposure to nitty-gritty of epsilons and deltas on the real line, but not so much abstract mathematics. In both Math 321 and 331, there's going to be a lot of both. So one difference is that in Math 331, I often try to emphasize a fair amount about how one might try to prove various statements. So I don't necessarily just say, you know, here's a theorem and here, now I'm going to start telling you the proof. I would normally try to ask the students in class if they have any ideas about how to prove it, which then sometimes takes longer, but then we spend more time trying to understand how you would come up with a proof rather than just writing it down. There are also times in which I might talk about additional proofs. So there are times in which I think it's interesting to give more than one proof of the same theorem. And so we might do that. Or in some cases, there are theorems that are sort of mentioned sort of a bit aside in the book, or are not really mentioned, that I think fits so well with the rest of it that I want to get into. So there are some theorems that I might get into that he doesn't. But at the same time, you know, there may be stuff that in the book that I might not get into that maybe he does. I mean, for instance, in chapter 3, there's a nice discussion of the irrationality of E. And, you know, students are welcome to read that. By the time we get to that point, hopefully you would have had enough background on all those things that you would understand what Rudin is talking about, but I probably won't be discussing it in the book. Another basic difference is, I think, in Math 321, there's maybe a larger probability that they will discuss sort of the theory behind calculus in some detail, like in chapters 5 and 6 of Rudin's book, really getting more to the theory of differentiation or integration. I'm less likely to do much of that in Math 331. One reason is a lot of the students may have taken Math 221, but that's not a prerequisite, so you definitely don't have to. But the other thing is that in my experience, even if you've had, most people would have had some idea of at least the heuristics for that. And after we've spent weeks or months talking in detail about limits and continuity and so forth, then getting into the precise details about derivatives and so forth, it's often relatively, you know, it might be a bit anticlimactic. Well, at any rate, so I should be curious. So let me emphasize again, I don't know exactly what Dr. Lukács is planning to do in the fall, and that may vary from semester to semester, instructor to instructor. I think often in Math 321, they have spent more time on that. Maybe there may be some question of exactly what they would do. I'm less likely to spend time on that, but I'm more likely to spend time, you know, time on additional proofs or proofs of sort of related theorems to say more about the theory behind compactness, if you're familiar with that, and how it's equivalent to various things. And I don't know if that's the type of explanation I'm supposed to give. Oh, and one other thing I might mention, especially related to the coronavirus the past year, because I wasn't quite sure how things were going to be in the fall. Last summer, I wrote some rather detailed lecture notes for the class, which are available in my web directory. And you can get to my web directory by going to the Math Department webpage, which you can presumably find through the university webpage or guessing what the Math Department webpage address looks like. And it looks like Dr. Nelson might even be checking on me now. And if you go to people and then faculty and then me, there's a link to website. And so there are various things there, but if you look at the notes called Math 331, so Dr. Nelson is now giving you the actual official address, and even maybe with the specific files, that math331.pdf. So I have other formats, but you probably, nowadays, I don't think anybody would care about that. But if you want to have some idea of what I would like, what I'm likely to do, that probably gives a fairly concrete idea. Of course, this upcoming fall is expected to be a bit different in terms of coronavirus and so forth. So hopefully I'll be able to use the whole Blackboard again. And stuff like that. So before, part of the idea is I wasn't quite sure with the video, how, if everybody was going to be able to read what was on the Blackboard, or, you know, I was going to have to erase the Blackboard a lot. And once, you know, I have to erase it more frequently than normal. So I wanted to make sure everybody had a you know, copy of what they could see. So things may be different this upcoming fall, given that I've already put those lecture notes on the web in great detail, and, you know, and we won't have some of the restrictions from the coronavirus, but that should give you some idea of exactly what I would do. And again, I can't say exactly how that might be different from what Dr. Lukács is going to do, but probably there will be a fair amount of overlap anyway. But.
Do you both use Rudin?
Yeah, so normally, I think, you know, as far as I know, so I think normally we've used Rudin's principles of mathematical analysis for both classes. And so as I say, the first chapter has a lot of stuff about the real line. I don't know how much he's planning to talk about that. I suppose you have the advantage that he's already addressed you and he may have told you, but so my guess, I certainly would normally review some of the main things having to do with the supremum and so forth. But some students may have seen a lot of that already in Math 302. So I would normally not spend a huge amount of time on that. I would at least mention some related facts. like the existence of the square root of a positive real number and so forth. But I would normally not get into the proof and just say, you can read about it in chapter 1 of Rudin's book. So I would normally sort of mention some of the highlights and things that I would be using a lot. But if you really want to get into detail, I would say go read it. And in some cases, maybe you've already seen it before. But so for me, I normally start in chapter 2. I often do things in a slightly different order than in Rudin's book. So I usually try to start with the definition of a metric space very early on. I'm sure Dr. Lukic would get into that pretty quickly, but in Rudin's book, he talks about countable sets before he talks about that. And I usually prefer to wait until one can see how it comes up. At any rate, a lot of students may have seen countability before in a class like Math 302. But I mean, that would be an issue with me compared to anything, that I don't exactly follow the book the way it is all the time. And so it amounts to largely the same thing, but sometimes I use different notation. I often do things in a slightly different order. I sometimes elaborate on some things and skip over other things. And so in the end, a lot of it is sort of the same, but at any rate, you can see a lot of that in the notes from my web directory.
I think that was helpful.
Are any questions about anything? I hope it's helpful.
Okay. Oh, and Professor Orkan, do you know, and Professor Sums, do you guys know how major advising works?
So I'm not quite sure what you mean by that. So in general, if you're interested, I mean, and you don't necessarily have to be a math major, if you want to talk to what I said, I think there's an official list of advisors that you can certainly contact for various reasons. One reason might be simply to talk about to talk about the math class, what math classes you might want to take, especially if you're trying to do a math major or a math minor. And of course, with the math major, there are 2 different types, the BA and the BS. There are also rules having to do with double majors and so forth. So I think you can talk to any of us about stuff like that. So I'm happy to talk to people about what classes to take. Sometimes students have tricky questions about some of the special rules about double majors and so forth. And I then recommend they talk to Frank Jones for the tricky questions. There are also issues about, declaring a major and so forth. But if the question was about like general advice of what might be a good class to take, or, what order to take the classes, so I came in time for some of the previous discussions. So, we have algebra classes in a certain order and topology classes in a certain order. To some extent, it can be important about which classes you've taken in what order before taking other classes. To some extent, not as much. To some extent, you can talk to the instructors of the classes and see if they'll let you in anyway, or
Oh, and then one other question that came up for you was if honors analysis turns out to be kind of too challenging, what is the drop back deadline? Is it 6 weeks or is it 2 weeks?
Oh, that's a good question. So one answer I would give is it's whatever the university says it is. So if the university changes what they say by at some later date, then it's whatever they say. So okay. Of course, so normally I think you can always, so of course you can drop normally by the end of the 7th week, but you can normally add by the end of the 2nd week. So I think that would be true for anything. But there are a number of classes in the math department, and I think in other departments as well, where you have sort of related classes and there are special rules to drop back from one to the other. So I think that I think there is a provision for dropping back from 331 to 221. I think it's probably before the 7th week, but I just want to be careful not to commit myself to that. Maybe Dr. Orkan knows that, some of these rules be tricky, and you can check the registrar's website, and especially since that's sort of a special case. It's not like for any other class. I would also say, just as general advice, I wouldn't necessarily recommend waiting until the last minute, because the longer you wait, the more complicated it could be. That whoever's teaching Math 321 might say, fine, you can switch, but of course I want you to make up the other assignments, or you would have to check with the other instructor about what that person wants you to do. I think normally they would be accommodating, but it's probably a lot easier to do it earlier in the semester. But at any rate, there is a system to do that. I mean, I think there are analogous things for 102 and 101, or 221 and 212. I think the rules are sort of uniform for all situations like that, and I think it's normally up until the 7th week. But
all right, so you can drop back. So this is not dropping the class, you are dropping back the course. So if you ask to registrar office just to make sure that in general, it was up to the 6th week, but due to the COVID, this was extended. So I don't know whether we are going to be going back to the regular schedule next fall or not, but it's always better to ask around the 5th week or so, just to make sure that you can drop back. And sometimes we are also accommodating students. I mean, let's say it is the 7th week, you pass the time. There is still chances. I mean, if you go to the registrar office and connect with the instructors, we can also accommodate this through the undergrad. There is this service that we can also help about. Okay, so please do not feel frustrated whenever you are, taking the classes. There is always, I mean, we are trying to help you also. Yeah.
Oh, and then another question in the chat for Professor Sems is, do you recommend looking at Spivak's calculus book to prepare for real analysis, or do you think it's okay if you just use Stewart or Frank's notes to use that as kind of preparation for real analysis instead?
So the point of Spivak's book being that it's more theoretical, or does more proofs?
I guess so. There's
I'm not that familiar with his calculus book. I know for instance, there's a famous book by Apostle that, I mean, so some books are more theoretical, and there's a famous one by Apostle. Of course, over the years, things have changed in terms of how much people talk about epsilons and deltas in basically like in a first calculus class or not. So I'm not sure exactly how to advise you, and I keep looking at the, well, somebody has a different question. I guess we'll come back to that. So certainly having some background or experience with more proofs, especially epsilon delta arguments, can help. On the other hand, in principle, certainly for me in 331, I can't say exactly what's going on with Dr. Lukács in 321, it might be similar. For me in Math 331, in some theoretical sense, we basically start over, that I will give definitions and so forth. But if you're not used to this kind of thing, you have to pay pretty close attention to all the epsilons and deltas and so forth. And if you've seen some of that before, that would help. But if not, in principle, it would all be there. At some level, when I'm advising students about what to do, one thing I would point out is it helps a lot to be interested in this kind of thing. If you're interested in the theory, then I think that makes it easier to keep track of this stuff, or to be more careful about it, because a lot of it is being careful about the details. If you're less interested in the theory, historically there are a lot of jokes about mathematicians, engineers, and physicists and so forth, and I guess these things have changed over time. But at any rate, it helps to be interested in that kind of theory. So even if you haven't had much background in it, if you're sort of interested in it, that can help a lot. But the flip side is, even if you've seen some of that, but you didn't find it particularly interesting, that might be a bit tricky. I don't know if that answers the question. But
I guess, the other point is that if 321 or 331 is too challenging this fall, the other option is to take 302, which is usually offered in the spring, which is like a bit more gentle.
That's certainly true. That so as you may all know, maybe this was discussed before, in our system, normally students are, so a student is automatically allowed to sign up for 321 or 331 if they have had, I think, 221 honors vector calculus, or 302 elements of analysis, or 354 honors linear algebra. And maybe also another option is or 220, the honors ODE class. So I think all of those are sufficient to allow you to sign up for it, meaning that the registrar's computer system will let you sign up for it. Of course, you can always contact the instructor and try to make an argument if you haven't had one of those classes. But I think Dr. Nelson's question is more about how in some cases it might be helpful to have taken more than one of those classes. It might be helpful to take all of them, I don't know. But certainly in the past, I think sometimes maybe students have made a point of taking 302 as well as 220, maybe have taken two of those classes, and maybe in part to be better prepared for 321 or 331. There's a new chat, undergraduate students.
Oh, sorry.
Oh, that's a different question. Okay, I'm just trying to keep an eye in case
Well,
something
I
else
have to go. It's very nice to see everybody, and good luck with